Hey folks, we're going to talk about Newton's second law, and I'll make a quick note about the previous video. So in the previous video, we talked about mass, which is a measure amount of stuff you are. It's in kilograms. We talked about inertia, which is an object's resistance to changes in motion. Mass is a measure of inertia. We talked about force, which is a push or a pull on an object. And then we kind of reviewed some of the forces you would have talked about last year. Normal force, which is perpendicular to the surface. So like if the ground is pushing up on you, the force of normal force would be perpendicular to the ground. You have the tension force, which would be a pull, like a string or even a person pulling on something. You've got friction, which is always parallel to the surface. Okay, and it opposes relative motion. We'll talk more about that later. And then we have the force of gravity, which is a little special for a couple of reasons. One, it's got its own little equation there. Force of gravity equals mg. And secondly, that's the only force that we're going to talk about now anyway that does not require contact. So if you drop a ball, the earth pulls on the ball, even if the ball is not touching anything. Okay. Now for all these forces, you can always make them into a sentence, and you should work on that as you go. So like for instance, the force of gravity, what that would be the earth pulls on you, pulls down on you. So your sentence can be structured noun, verb, adverb, direct object. So earth pulls down on you. Okay. So as we do examples, I will make some notes of that. You want to get the hang of writing the forces in sentences like that, because that's going to be important when we talk about Newton's third law. Now, Newton's first law says things want to go in a straight line at a constant speed unless acted upon by a net external force. So it's important to understand things want to go in a straight line at a constant speed. Now, by the way, at rest, it's just a special case of a constant speed. It's a constant speed of zero. So Newton's second law is the unless part of Newton's first law. And whereas Newton borrowed heavily from Galileo and Descartes for his first law, the second law is pretty much on Newton. Okay. Now, the version that we use is not actually exactly how he wrote it, but we're going to use this first version that I'm going to talk about. I will mention the way Newton actually wrote it in the subsequent unit. But here's what Newton's second law would say if you were going to write the words down. And by the way, I would not write the words down, but here's what it would say. It would say something like, if a net force acts on an object, the object will accelerate. And the acceleration of the object is proportional to that net force in the same direction as that net force and inversely proportional to the mass of the object. Now, we don't write the words down because the equation is way easier. If a net force acts on an object, the object will accelerate. And the acceleration of the object is proportional to that net force in the same direction as that net force and inversely proportional to the mass of the object. So that's Newton's second law. Now, you may have seen it written before from previous course, F equals ma. Well, first of all, that's wrong. Force does not equal ma. Net force equals ma. So that's very, very important to understand. And then technically, there should be vectors over these because whatever direction net force is, that'll be the direction of the acceleration. So notice now we have the same equation, so you can use either version of it. Now, a quick reminder what net force means. So a real simple example. Let's say I had a force of 10 newtons to the right and a force of 3 newtons to the left. If I were to vectorially add those forces, that would be 7 newtons to the right. Okay, so that's what we mean by net force. When you've added up all your forces, if the answer is not 0, then the object's going to accelerate. And it's going to accelerate in the direction of the net force, meaning in this case, this object would accelerate to the right. Now, the object would either be moving to the right and speeding up, or the object could be moving left and slowing down. That's still a rightward acceleration. Now, we have now left the realm of kinematics. Kinematics was the first several chapters. We talked about motion and what kinds of motion there are. So we talked about linear motion, horizontally and vertically, free fall. Then we talked about two-dimensional motion, so like projectile motion, circular motion, relative motion, and so on. Now we're delving into what we call dynamics, and that's the reason why and how things move, okay? So things will accelerate if you apply a net force to them. And actually, we will also talk about statics. If, as a matter of fact, if you go into engineering or something like that in college, like, mechanical engineering or civil or aero, you'll have a whole course called statics. And statics means not moving. So in this equation, Newton's second law, A is always 0 in statics. And it's still a pretty hard course. And then dynamics, A is not 0. Okay. Now, the last thing I'll for an intro to Newton's second law, and then the next video I'll start with some good examples. But this last thing, intro part of this is FBDs. And again, this is a second year course, so you would have had talked about FBDs last year. I'll do a brief review here. So first of all, FBD is short for free body diagram. And what that means is take the body, and that just means an object, car or whatever you're analyzing, and free it from its surroundings. So draw the car or whatever it is by itself. And then in place of the surroundings, draw the forces that the surroundings provide to that body. Okay, so that's what free body diagram means. So I'll do a couple simple ones just to kind of get you going. And then on examples in the subsequent videos, we'll draw pretty complicated FBDs. But let's say you're standing still on the ground, and I ask you to draw an FBD of you. So first I'll draw a little sketch. Now this is not an FBD, this is a sketch. There's a sketch, okay? If I were to draw an FBD of you, okay, so you first of all, you just draw a dot, okay? That's you. And it's not an art class. And then you say, what do the surroundings do to that person? Well, first of all, you're on Earth, so the Earth is going to pull down on you, and that's the force of gravity, okay? And then now that doesn't require any contact. So basically, anything on Earth, you're always going to have that straight down force of gravity. And then you look to see, hey, what is touching the object? Well, in this case, the ground's touching the object. The ground is going to push up on the person, and that's your normal force, okay? And if you're standing still, that's going to be it, okay? Now, a second one, you got to be careful about like which object you're drawing the FBD for. So let's say that, I'll do a little different one now. Let's say that there's an elevator, okay? And it's being held up by a cable, and then there's a person in the elevator, okay? And just for the sake of argument, let's say the elevator is accelerating upward. So you're speeding up upward, okay? Let's first draw an FBD of just you, okay? All right, so I'll draw my dot, okay? We know there's a force of gravity acting on me, okay? The Earth's pulling down on me. And then what other forces act on you, the passenger? Well, a common error here is for people to draw a tension force from the cable. And that's not acting on you. The cable is not touching you. You only look for the things touching the person. Well, the only thing touching the person is the floor of the elevator, which would be a normal force. So the normal force acts up on that person, okay? And that's it. That's the only thing touching the person. Now, are these forces equal? No, not in this case, because you're accelerating upward. So we know that Fn is going to be greater than Fg in order for you to accelerate upwards. So as a matter of fact, I'll even amend this slightly. I'll draw this arrow a little longer just to kind of signify that fact. There you go. So now, by the way, if you're accelerating upward, you're doing one of two things. You've pushed the button, you're at the bottom of the elevator ride, and you've pushed the up button, and you're starting to accelerate upward for the first, whatever, couple seconds of the ride. And during that first couple seconds, you feel heavy. And that's because we don't feel our weight. We don't feel Fg. We feel the normal force. And the normal force is bigger than your weight, so you feel heavy, okay? Now, the other example of accelerating up would be if you're moving downward, but the elevator is slowing down. So like at the very bottom of the ride on the way down, you feel heavy again. That's also an upward acceleration. The FBD would be identical. From the FBD alone, you wouldn't know which of the two motions you're having, okay? If you're moving at a constant velocity or you're still, that Fn and that Fg will be equal, okay? Now again, I'll repeat that. If you're still or if you're moving at a constant velocity. If you're moving at a constant velocity, you have no acceleration and your net force would have to be 0. So if you're moving at a constant velocity and that FBD we just drew, your Fn and Fg would be equal. And by the way, you'd feel normal. So during most of an elevator ride, you feel normal. Okay, you feel average or regular. Now, the other FBD we'll draw is of the elevator, just the elevator. Okay, so here's the elevator. Now it has a force of gravity acting on it, which is different than the person's weight. Okay, so I'm going to label that FG2. Okay, that's different than FG, so I got to make sure I label them different. So that's the weight of the elevator itself. Now, what else touches the elevator? Okay, well, first, there's a cable touching the elevator, so there's force of tension, okay, from the cable, which should be bigger than the F of gravity here, but for now, I'll just leave it like that. And then what else touches the elevator? Well, the person. Now, the person's going to press down on the elevator, so you put a second arrow next to the first, that's down. What do I put there? What do I put? Well, it's not FG of the person, and that's a common error that people make too. They'll say, oh, the force of gravity of the person. No, it's the normal force of the person acting down the elevator. Okay, so in the first FBD of you, the elevator pushed up on you. In the second FBD, you pushed down on the elevator. Okay, same force. And by the way, this arrow and this arrow will always be the same size. Okay, in these two FBDs, no matter what the elevator and person are doing, those two arrows have to be the same size. Now they're not drawn that way here, but they should be the exact same size. Okay, so again, when you're drawing FBDs, be very careful what system you're drawing. Okay, are you drawing you? Are you drawing the elevator? Now, if you drew both together, okay, then you would have the cable, and then you would have FG plus FG2. That would be the force of gravity acting on the person plus the force of gravity of the elevator. So the total weight of person and elevator combined. So you really have to be careful when you're drawing FBD, like which system are you drawing? All right, starting with the next video, we'll just do a lot of examples, and I hope this was helpful. Thank you very much.